Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held in the month of March 2025. It is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section Linear Algebra, which is related to the Primary Decomposition Theorem. This question is placed in part C, which is a multiple select question. There may be more than one answer. The question carries 4.75 marks. And the question ID is 706554. Further, this question is suitable for all these examinations. Right. The given question is, let T be an R linear transformation from R power 4 to itself. Assume that the characteristic polynomial of T has two distinct monic, irreducible, quadratic factors q1x and q2x. Which of the following statements are true? We are given four options. Option 1. There exists a non-zero vector v belongs to R to the power of 4 such that q1 of t operating on v is equal to 0. Option 2. There exists a non-zero vector v belongs to R to the power of 4 such that q1 of t operating on v is 0 and q2 of t operating on v is equal to 0. Option 3. For all non-zero v belongs to R to the power of 4, v and t of v are linearly independent. Option 4. If q1 of t operating on v is 0, for some non-zero v belongs to the R to the power of 4, then v, the set consisting of v, t of v, t square of v and t cube of v is a basis of R to the power of 4. Right. Let's now discuss the solution of the problem in detail. We are given a linear transformation T. It is a R linear transformation T from R power 4 to R power 4 to itself. We are given the Cauchy polynomial chi t of x has two distinct, they are different, monic, the leading coefficient is 1, irreducible, quadratic factors q1 of x and q2 of x. That is, chi t of x is the product q1 of x into q2 of x, where each qi of x, that is q1, q2, they are irreducible over R of degree 2. Agreed. Since q1 of x and q2 of x are irreducible over R, that means these polynomials, these factors do not find roots in R. They are irreducible over R. Their roots must be complex conjugates. So the characteristic polynomial chi t of x has no real roots. This implies the transformation T has no real eigenvalues. It's a very important byproduct and it is necessary for us, and we will use this fact in one of the options. Since both factors chi t of x are irreducible quadratics over R, what can we say about the minimal polynomial mt of x? It will also be divisible by q1x and q2x, and thereby the minimal polynomial of t will be, the characteristic polynomial of t will be the product q1 of x into q2 of x. Right. Once we see this scenario here, we remember a famous theorem. That famous theorem is Primary Decomposition Theorem. Right. What is Primary Decomposition Theorem in linear algebra? Let V be a finite dimensional vector space over a field F. Let T be a linear operator on V. That means it's a linear transformation from V to itself. If the minimal polynomial of T factors into distinct monic irreducible polynomials over F as mt of x is equal to p1 of x to the power of r1, p2 of x to the power of r2, etc., pk of x to the power of rk. Each is a monic polynomial, mt of x, the minimal polynomial of t, it factors into distinct monic polynomials. These are monic polynomials and irreducible polynomials over F. Right. Then the vector space V can be expressed as the direct sum of the subspaces Wi, where that is Wi, that is V is equal to W1, the direct sum with W2, plus circle, etc., plus circle Wk, where each subspace Wi is the kernel of the operator pi of t to the power of ri, r suffix I. That is, Wi is the kernel of pi of t to the power of r power ri, pi of t to the power of r suffix I. Right. The furthermore, each of these subspaces Wi is t invariant. This we are not using yet. And the minimal polynomial of the restriction of the linear operator t to the subspace Wi, the minimal polynomial of the restriction of t to this subspace is precisely that polynomial pi of x to the power of r suffix I. Right. So what we want is this one only. So we go back to our situation, and this is what we have done. The minimal polynomial of t is the product of q1x and q2x, where q1x and q2x are distinct monic irreducible quadratic factors. Right. By the primary decomposition theorem, r to v means r to the power of 4 is equal to W1 direct sum with W2, where Wi is the kernel of Qi of t. Qi of t. Right. We continue in the next slide. Option 1. There exists a non-zero vector v belongs to r to the power of 4 such that Q1 of t operating on v is 0. We have r to the power of 4 is the direct sum of two subspaces W1 and W2, where W1, W2, Wi is the kernel of Qi of t. Note that the dimension of W1 is the degree of Q1 of x, that is 2. So when the dimension is 2, its kernel W1 is equal to the kernel of Q1 of t is not trivial, because its dimension is 2. Is not trivial. When it is not trivial, there exists non-zero elements in W1. So there exists non-zero V belongs to R to the power of 4 such that V belongs to the kernel of Q1T. That is, Q1 of T operating on V is 0. So there exists a non-zero vector V belongs to R to the power of 4 such that Q1 of T operating on V is 0. Thus, our option 1 is true. Okay, let's get into 2. There exists a non-zero vector V belongs to R to the power of 4 such that Q1 of T operating on V is 0 and Q2 of T operating on V is 0. If this is true, then we will be in, okay, let's argue. We have R to the power of 4 is the direct sum of W1 and W2, where Wi is the kernel of Qi of T. R to the power of 4 is W1 plus R till W2 is same as R to the power of 4 is equal to the sum of W1 plus W2, and W1 intersection W2 is the trivial, that is the zero vector alone. Assume that there exists a non-zero vector V belongs to R to the power of 4 such that Q1 of T operating on V is 0 and Q2 of T operating on Y is also equal to 0. This means what? V belongs to the kernel of Q1 of T. What is kernel of Q1 of T? That is W1. And V belongs to the kernel of Q2 of T, that is W2. That means a non-zero vector V is present both in W1 intersection W2. It is present in both in W1 and W2. But we have W1 we have W1 intersection W2 consists of only zero vector alone. That means there exists a non-zero vector V belongs to R to the power of 4 such that V belongs to W1 intersection W2 is a contradiction to the fact that W1 intersection W2 is just consists of only zero vector alone. But here what you are saying is there exists a non-zero vector V. Is a contradiction. This contradiction is based because of your assumption. Therefore, your assumption that there exists non-zero vectors V belongs to R to the power of 4 such that these two things happen is not true. Therefore, option 2 is not true. Agreed. Agreed. We continue in the next slide. So far, only one option is true, that is option 1. Option 3. For all non-zero V belongs to R to the power of 4, V and T of V are linearly independent. Assume the contrary. That means the set consisting of V, T of V is not linearly independent, so to speak, that it is linearly dependent over R. For all non-zero V belongs to R to the power of 4. This means T of V is a scalar multiple of V. This means there exists a scalar lambda belongs to R such that T of V is lambda into V. It means lambda belongs to R is an eigenvalue of T, which is a contradiction. Why? We have seen in the beginning itself, all the eigenvalues of T are complex, they are not real. We have seen the transmission T has no real eigenvalues. This is a contradiction to the fact that T has no real eigenvalues. Therefore, option 3 is true. They are not linearly dependent, therefore it's linearly independent. Our assumption is wrong. Option 4. if q1 of t operating on v is 0 for some non-zero vector v belongs to R to the power of 4, then the set consisting of v, t of v, t square of v, tq of v is a basis of R to the power of 4. Let q1 of x, because it is a quadratic factor, x square plus ax plus b. Because it is monic polynomial, the coefficient of x square is 1. For some ab belongs to R. Right. We have q1 of t operating on v. For some v not equal to 0 belongs to R to the power of 4 will imply t square plus at plus bi operating on v is equal to 0. Yeah, this is true. This is true. This is true. This is true from option 1 itself. Right. So that means t square of v is minus a times t of v minus b of v. That means t square of v is a linear combination of v and tv. So that thereby the set consisting of v, tv, t square v, t cube v is not linearly independent. Right? T square v is a linear combination of v and tv, and thereby this becomes linearly dependent, is not linearly independent, thereby it cannot qualify to be a basis. Therefore, this set is not a basis of R to the power of 4. Therefore, the option 4 is not true. So far, option 1 and option 3 are true. The answer to this question is options 1 and 3. That is the detailed discussion of the solution of the given problem from the section Linear Algebra, which makes use of the primary decomposition theorem. And this theorem is very, very important. Please concentrate on primary decomposition theorem and some problems thereon and make a very good notes. I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure we are going to meet you, all of you, once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.